Hello everybody! In this video lecture, you will learn about Newton's third law and how to identify action and reaction pairs. Check out this comic strip. Turns out he is 100% right. The wall hit him and caused him to get hurt. We think that our actions affect us. In fact, our actions affect other objects. In this situation, his action, his hitting the wall, probably caused the wall to get dented. But the reaction, the wall hitting right back, caused him to get hurt. Newton explained this in his third law of motion. Whenever an object exerts a force on a second object, which is called action, the second object exerts an equal and opposite force to the first object. This is called reaction. There are three important points to understand about Newton's third law. The first one is, there is no single force. Forces always come in pairs. To every action, there is an equal and opposite reaction. When action is A exerts force on B, the reaction is simply B exerts force on A. Let's learn how to identify action and reaction pairs by working on some examples. Here is the action. Tire pushes the road. We show this by drawing an arrow on the road and using the subscripts F for tire pushing on the road, FTR. What is the reaction to that? The reaction is the road pushes the tire. Therefore, I need to draw an arrow on the tire and show this as force of road on the tire, FRT. We know that by Newton's third law, F of road on the tire is equal in magnitude and opposite in direction to F of the tire on the road. Now, here is another example. Action is earth pulls the ball. So we draw an arrow on the ball and label it as force of earth on the ball, FEB. What is the reaction? The reaction is force of ball pulling on the earth. So we draw an arrow on the earth and we label this as force of ball on the earth, FBE. Just like before, force of earth on ball is equal to force of ball on earth. And here is another example. Action, rocket pushes gas. So an arrow drawn on the gas, force of rocket on the gas. And the reaction to that would be gas pushing the rocket forward. So I need an arrow on the rocket and label this as force of gas pushing on the rocket. But wait a minute. If these forces are equal in magnitude and opposite in direction, why don't they cancel? Well, action and reaction forces never act on the same object. Therefore, they won't be canceling each other. Here is how. A football is kicked. There's a force on the football. So, here is force of A on B. Well, there's a reaction to this. There's a force of B on A. There's a force of B on A. If we isolate the ball and call it our system, here is our ball. This is the system. You can see that there is only one force acting on the ball, and there is nothing to cancel it with. And if you look at on the foot as the system, so here it is, only the foot. There is only one force acting on foot, and there is nothing to cancel that one either. Now check this case. Ouch. That looked painful. In this case, there are two pairs of action and reaction forces. Here is the first pair. There's a force of A on B, and the reaction to that is there's a force of B on A. As you see, they don't act on the same object. And the second pair is there's a force of C acting on the ball, and reaction to that is there's a force of B acting on the foot C. These are also action and reaction forces, and they don't act on the same object and they don't cancel. But if you take a look at only at the ball, like this, how many forces do you see acting on the ball? There are two forces, and if these forces are equal in magnitude, they will cancel, and the net force on the ball can be zero. But these forces are not an action and reaction pair. Therefore, an action and reaction force can never act on the same object and won't cancel each other out. Okay, I get it. The forces are not canceling out and they are equal. But if the forces are equal, how come they create such different results, such as the ball fly forward and the foot moves only a little? It turns out a given force exerted on a small mass produces a greater acceleration than the same force exerted on a large mass. Just like Newton's second law says, acceleration depends on net force and the mass. Check this out. A cannon fires a cannonball. We have a pair of action and reaction forces. The action, cannon pushes ball, FCB, and the reaction, ball pushes cannon. These forces are equal in magnitude and opposite in direction. Forces are the same, yet the resulting motion or acceleration is not. The same force exerted on a small mass, such as the cannonball, will create a larger acceleration compared to the same force acting on the much larger mass of the cannon. Okay, let's solve an example problem. A man and a woman are standing on ice. The woman pushes on the man with a force of 45 Newton due east and there is no friction. We need to draw a free body diagram and determine the acceleration. Well, we have two objects, so better start with drawing them. So here is a box for man, and here's another box for woman, and this is the surface. So now first the action force. Woman pushes the man to east. So here we go. There's a force arrow drawn on man and force of woman on man drawn this way. And there will be a reaction to that, right? So the reaction force will be force of man on woman. So here you go, force of man on woman. There you go. Now to finish the free body diagram, we have to consider the vertical forces as well. So we have normal and gravity acting on woman. Similarly, normal and gravity acting on the man as well. Now you see that these vertical forces are not going to change the motion at all, because even though the normal forces are different for women and men, they are each individually balanced, so they are not going to create any acceleration. So let's continue with writing down the rest of the given. So masses are given. So mass of the woman is 48 kilogram and mass of the man is 82 kilogram. And we know the action force of woman on man is 45 Newton. But we know from the Newton's third law, action and reaction forces are equal in magnitude. So with this information, we can easily solve the acceleration using the second law. Right? Acceleration of the woman is equal to net force of the woman divided by the mass of the woman. So plugging in the values, 45 over 48, checking this in calculator, we can find that this is 0.94 meters per second squared in the west direction. Same for the man. applying the second law, acceleration for the man is net force over mass for the man. And this time the values are same force, 45, but different mass, 82. So checking this out on the calculator, we find that it is 0.55 meters per second squared to the east. So these are the initial accelerations, and they last as long as they keep on pushing one another. And as you see, different masses create different accelerations, even though the forces are the same. Now consider this situation. We have a mass 1, let's say 10 kilogram, and a mass 2, let's say 5 kilograms, sitting next to each other. And we push the big box with an applied force of, let's say, 60 newtons to the right. Okay, so they are going to move together, but there is also friction with the ground. So let's say here is the friction force for the first one is 20 Newton. And since the second one is half as massive, it should have half the friction force, right? So then it should have friction to 10 Newtons. All right. So these two are going to move to the right. And our question is, what is the force they exert on one another, the action and reaction forces? So what is the force of 1 on 2? What is the force of 2 on 1? Now, in order to solve a problem like this, the first thing you need to know is acceleration. And the easiest way to figure out the acceleration is assume these two are like just one object. Here it is. So it is a weird shape object such as this one. Now, what would be the forces acting on this one? So there will be an applied force and gravity and normal and the combined friction forces, right? Together they make 30 newtons. Now, how do we find the acceleration for this? Well, the vertical forces are obviously going to cancel out, and let's find the horizontal acceleration by writing the net force equation, right? So acceleration by the second law, acceleration is equal to net force over mass. And net force is, let's say to the right is positive, the applied force minus friction divided by the mass. So plugging in numbers, applied force is 60 minus 30 divided by the total mass 15 gives us the acceleration of 2 meters per second squared. Okay, now we know the acceleration of them together and also separately because they are moving together. Alright, in order to find the action and reaction forces, I am going to draw a more detailed free body diagram, but this time I will draw these boxes a little bit apart so that the diagram won't be too messy. Alright, so let's see. For the first one, we have the applied force, and we have the friction force. We have force of normal and mg. Similarly, we have friction force and normal force for the smaller box, and we have the force of gravity as well. Now, we know that we are pushing the big box, but what moves the little box? It is not our push, right? Because remember how we talked about objects are not psychic? So the small box is going to move because the big box will push it. So this means the force of 1 pushing on 2. That makes it move. Well, if this is the action force, there must be a reaction to this between the two of them, right? So in reaction, the little box is going to push the big box back, and it is going to make it a little bit harder to move, which is logical, right? Okay, now using this, we can write an individual net force equations for each mass to figure out what forces there are. So let's do that for the first one, the big one first, M1. For M1, and again we are going to do this for horizontal because acceleration is expected to be only on the horizontal. So the net force is going to be applied force minus, well, minus, there are two forces, F21 and F friction 1, and that equal to M1A. And all I have to do now is to rearrange to isolate F21 and plug in values. As you can see, the force of 2 on 1 is 20 newtons. Well, I expect a force of 1 on 2 should also be 20 newtons, but let's double check. Let's write a net force equation for M2 this time. Net force X is F12 minus friction 2 equal to M2A. Alright, plugging the values. And here we have it. F12 is also equal to 20 newtons, just like Newton's third law predicted it.